Hello and welcome to lectures on state space approach to control system analysis and design. Now we will be discussing controllability. So far we discussed standard state space representation of dynamical systems, solution of state equations, equivalent mathematical models, representation of state equations to transfer function, representation of transfer functions to state equations. We covered a little about simulation and numerical solution of standard state space equations. Now, whatever we did so far was something which was also being done in conventional control, and we did these things in the perspective of, in the framework of standard state space representation of systems. However, now the topic which we are going to discuss, the controllability, and the subsequent topic, observability, these are distinctive concepts which are only to the framework of state space methods. They do not belong to the conventional control methodologies. Subsequently, however, there have been attempts to adopt these concepts, controllability and observability, also through the transfer functions. So these concepts, these ideas were introduced in mid to late 1950s and early 60s. There have been a lot of research in this, pioneered by Rudolf E. Kalman and some other researchers like Gilbert. Today's lecture is aimed at understanding the concept of controllability as introduced by Kalman. In this lecture, we will cover the definition of the controllability, how it is defined, the interpretation of state transfer, because we will see that the definition of controllability involves state transfer. So we have to do some interpretations about the state transfer and the Kalman controllability criterion. Let us proceed ahead. We begin with the definition of controllability. A system described by the state equation x dot t equal to atxt plus btut is said to be controllable if and only if it is possible by means of the input to transfer it from any initial state xt0 to any terminal state xtf at time tf within a finite time of tf minus t0. Now, first of all, this definition involves the matrices A, T. That means we are discussing linear general case, the time varying case. The controllability applies to linear systems, time varying in general, time invariant also, as we will see. So it is specific to linear time varying system and it doesn't apply to nonlinear systems. We should keep it in mind. The other thing is that these particular words, any initial state, the sense of any here is all. In the state space, the system can be at any particular coordinates at the given time t0. So the state transfer has to happen from any of those various points in the state space which exist. So this any means all. Anything one thinks of, that can be the initial state. Similarly, the terminal state xtf can also be any point, any coordinate in the state space. So what it means that any all the points in the state space which one may think of, from there to all other points in the state space one may think of, the state transfer should be possible. So any implies all the various points. If there is any particular point, maybe one single point, from where the state transfer could not be possible, or if there is any one point to which the state transfer could not be possible, then the system will be uncontrollable. The definition is very strict. Even one point where the state transfer is not possible, even one point from which the state transfer is not possible, if they exist, system will be treated as uncontrollable. Other thing is that the time involved for achieving the state transfer should be finite. Then only the system will be treated as controllable. Otherwise, if the time taken is infinite, it can be large, but it cannot be infinite. So if the time taken is infinite, the system will be considered as uncontrollable. The other thing is that what we see, if we read the definition once again, controllable if and only if it is possible by means of the input. I want special attention to this phrase, by means of the input. So we are utilizing the input, the effort, and what we are doing, we are transferring the state from initial value to some final value. So it is a connection between the input and the state. It is a kind of coupling between the input and the state. It doesn't involve anything else. Then this property is generic. The controllability is a generic property. We will see when we solve some numerical examples that the controllability depends on the particular values of A and B. Slight changes in some elements of the matrix A or the matrix B may render an uncontrollable system to become controllable and a controllable system to become uncontrollable. It is possible. The other thing is that the input is the means to achieve the transfer. But even though we realize that in physical systems there are constraints on the input, but in this definition the input is totally unconstrained. There is no constraint on input. Means that even though in real physical situations the input, magnitude of the input has to be limited. For example, the voltage may have to be limited by 5 volt or 12 volt. It has to be within plus minus 5. It may not vary so fast. But in this case, when we discuss controllability, we don't think about any of such constraints. Neither the magnitude of the input is limited, nor its rate of change is limited. So it is only the input, some kind of input that has to exist, some kind of input variation that has to exist to achieve the state transfer. And then the system will be considered as controllable. If a system is controllable, what is the benefit? So we will see subsequently the controls can be designed to meet all the various kinds of specifications only if the system is controllable. So it's a kind of guarantee. The controllability is a kind of guarantee that by applying particular type of input, a desired behavior from the system can be achieved. So it is a useful property which is required for design of controllers for the system. if the system turns out to be uncontrollable, let us say some state transfers are not possible to achieve by application of input. There are some combinations of initial conditions and terminal states which do not belong to the category of achievables or where the state transfers will be possible, then the system will of course be uncontrollable. But does it mean that the given dynamical system is useless system? Should it be discarded? These kind of questions may arise. And obvious answer to this is that yes, the system may not perform in the desired manner, but it may not be useless. It may still meet some of the performance specifications. There may be some limitations on its performance, but it's not true that uncontrollable systems are useless systems. They may still be quite useful. Now, the definition of controllability involved the phrase state transfer, and we will interpret this phrase little elaborately. So we are given with the system which is x dot t equal to atxt plus btut, and the initial condition is specified is xt0 at time t equal to t0. Now we have solved this state equation in some earlier lessons, and we see that the solution of the state is given by this expression. Xt is state transition matrix evaluated between t and t0 pre-multiplied to xt0. This is the zero input response plus the zero state response, which is given by this integral of the state transition matrix evaluated between t and tau multiplied with b tau, multiplied that with u tau integrated between t0 to t with respect to tau. So the state at any time is summation of the zero input response and the zero state response. Now let us say that, so from this at the terminal time t equal to tf, the state xtf can be given like this. We have substituted in place of t, tf everywhere, and we get this expression. Now let us say by coincidence it so happens that the desired terminal state is exactly this, which is the equal to the zero input response of the system at time tf. Suppose it's coincidentally it happens that specification is this, then obviously we see that this belongs on the natural trajectory. The natural response itself meets this state xtf is on the natural trajectory of the system starting from xt0. So at time t equal to tf, the system starting from t equal to t0 will pass through that state xtf, and in the specification is same, then anyway it happens, and that means that no input is required to achieve this state transfer. It is happening anyway, but that is very trivial. That may happen only in very specific situations and very coincidental. The general situation will be like this, that the terminal state will not be equal to the zero input response. It will be different from that, and this difference is something which has to come through the application of input. What we mean is that the system state xt0 was here in the state space. This is the xtf, let us say, and this has to be achieved. So from this, one component is coming from the zero input response, natural response of the system, and the remaining has to be supplied by application of the input. So as we saw that integral, this contains the product phi into b, and the input reaches to make to the component of xtf through that the product of phi t into bt, phi t tau into bt. So what it means that this phi t tau b tau should have certain property, and that property is this, that the rows of this n by n matrix phi t tau b tau should be independent over the given time interval of t0 to tf, both the ends inclusive. So if these rows are independent, then the input will be able to contribute to the desired terminal state of the system, and this independence is given by this n by n matrix denoted by W, evaluated between t0 and tf. It is given by this integral, and it is called as the controllability Gramian. It looks difficult but easy to remember, because this is phi into b and this is the transpose of it, phi b into transpose of phi b, the whole product, which becomes phi b, b transpose, phi transpose, integrated with respect to tau, and has to be evaluated between the limits t0 to tf. So the state transition matrix of the system pre-multiplied with the input matrix, that multiplies to transpose of the input matrix and the transpose of the state transition matrix, whole thing integrated between t0 to tf, that gives the controllability Gramian matrix W. And if this matrix is non-singular, then the system will be controllable and all the state transfers will be possible. Nothing will be left. Any initial state to any final state, the state transfer will be possible within the interval of t0 to tf. Any t0 and any tf, any xt0 and any xtf. The time can be small, the time can be large, but the interval t0 to tf, that will be finite. This will be possible, and it also gives a way that what that input can be. So once we have that W which is non-singular, then the input can be calculated using this expression. This part is the component which has to come through that integral, and this is being pre-multiplied by W inverse, and that is being pre-multiplied by B transpose, phi transpose. So this input, if applied, will achieve that required state transfer from xt0 to xtf. The point in state space x0 to the coordinate in state space xtf. That state transfer will be possible. Now we see what happens in case of linear time invariant system. Because the state transition matrix in case of linear time invariant system is given by the matrix exponential, phi t tau is e power a t minus tau, phi tf tau is a e power a tf minus tau. So controllability Gramian, in place of phi we get this matrix exponential, and it gets further simplified like this: 0 to tf minus t0 e power a tau b into its transpose. B transpose e power A transpose tau d tau. This becomes the matrix W in case of linear time invariant systems. And of course, the input accordingly becomes like this. In place of phi, we have matrix exponential e power A t of minus tau and e power A t transpose t of minus tau. And using this formula, the input can be calculated. Using this formula, the matrix W, the controllability Gramian, can be calculated, and then the state transfer, that input can be determined for the given xt0 to given xtf in the given time t0 to tf. We see with the help of one example. This system is of course simple system given in the diagonal form. One of the eigenvalues is minus half, other eigenvalue is minus 1, and this system has this input matrix. We have to determine an input ut which needs to be applied to transfer the system from 10 minus 1 at t equal to 0 to 0 0, the origin of the state space, at t equal to 2. So t0 is 0, tf is 2, and this is x0, xt0, and this is xtf. This is xt0. So we have to calculate, and of course the question, it is very clear from the question that this system is controllable. That is why it is asking for the input which can be applied to transfer the system. Nevertheless, we will check, we will evaluate W and we will check whether it is non-singular or not. So we will calculate this WTF T0, which in this case is W20, and we will check its rank. So it will be given by this integral. This is phi t tau, t of tau. This is B transpose, and this is phi transpose, to be integrated between the limits 0 and 2 over time dt. And when it is integral is done and the value is evaluated at time 2 and 0, we get it like this, and when the numbers are evaluated we get like this. So we get WTFT0 as this matrix, and we can calculate its determinant. We see that the determinant is non-zero, meaning that W is non-singular, and its rank is 2, and 2 is also the order of the system. So the condition for controllability and state transfer, they are satisfied. So this is the W inverse which comes, and then we can, the next step will be to evaluate phi tf t0 x0. So of course phi has to be evaluated using the matrix exponential e power A tf minus t0. Tf is 2 and t0 is 0, so e power 2a. We are given a, so phi t of t0 can be evaluated. Multiply that to x0 and we get this. So the input ut will be given by, this is x0, this is phi t0 x0, and this is the this quantity phi t0 t0 x0, this is this, and this is xtf, the final value. W inverse we have calculated. This is that in the expression the phi was there and B was there, B transpose and phi transpose, they are there, they have been all substituted, and so we'll get that this input will achieve the given state transfer from something like 10, 1 to 0, 0, the origin of the state space. From this to this, the state transfer will be possible by this input, which is combination of two exponents. There is one exercise for the students. You can take this system. The example which was solved is a diagonal system. It is not diagonal this time. The input matrix is this, and it is given that t equal to 1, the state is 1 minus 1. So it is the xt0. This is xt0. And it has to be taken to x2. This is xtf. So tf is 2 and t0 is 1. This is xt0, this is xtf. And first of all, it has to be shown that the system is controllable by calculating w and inverse of w, and then the input ut has to be evaluated, which will achieve this state transfer. So you can sharpen your mind by trying to solve this example using the concepts presented so far. We summarize. Controllability is an important property for the controller design for linear systems, linear dynamic systems. Kalman's controllability criterion based on rank of the controllability Gramian is useful for testing controllability of all the various types of systems, time varying as well as linear time invariant. Of course, only the linear systems. And over and above that, it gives a method for determining the input required for achieving the required state transfer. So it determines the controllability. Once the controllability is established, the answer to state transfer is yes. All the state transfers will be possible, and it gives the expression for determining the input over the interval t0 to tf, initial time to final time. Thank you. We'll meet once again in another lecture.